All right, welcome back, folks. Hopefully everyone's okay. Let's get right into it. And I want to continue on with where we left off with yesterday, and that was being able to take a chemical reaction, take a chemical equation that describes a chemical reaction, and converting the coefficients and using those coefficients to obtain masses. All right, so we did number six here yesterday. And we interpreted this equation in terms of atoms and molecules. So we were able to do the first part. We were able to do the first part of the of this problem yesterday. Today, then, I want you to take about 5 minutes. You take about 5 minutes, and I want you to work through these problems and interpret this equation in terms of moles and masses. Okay? And so, what you have to make sure you remember here, and this will give me an opportunity to review with you folks what to do here, and that is you have to remember the balance equation. And we did this in the POGO activity. The balanced equation gives us the coefficients, gives us the number of atoms. We can go ahead and do a really simple quick calculation to see how that's a number of counting atoms in that case. It gives us the number of molecules. And remember, when we use the term molecules, we're referring to the number of particles in the reaction itself, both reactants and product. And so the coefficient gives us the number of particles directly, and also it gives us the number of moles involved in the reaction directly as well. However, when it comes to masses, though, we have to do a simple calculation first in order to get the masses. And the reason why we want to obtain the masses is because, remember, we cannot measure out moles. We definitely can't measure out single individual atoms and molecules, but we can't measure out moles. There's no tool, there's no instrument that we can use that measure out moles. And so we have to be able to convert the information, convert the coefficients, and convert the number of moles into masses. Okay? And so we learned back in chapter 10 how to do a moles to mass conversion using the molar mass. And so what I would like you to do, take about 5-ish minutes to get this done, okay, is I want you to do the calculations here. For these two balanced equations, I want you to find the masses involved in this in these two chemical reactions. Okay? And so once you get back, we'll work on these together, and then we'll continue on. And we'll talk about how we can obtain information about volumes from a balanced equation as well. Okay, so take about 5 minutes, work on finding the masses of these two, and then when we get back, we'll go over them together. Okay, go ahead and get that done, folks. Okay, let's go ahead then, and let's take a look at what we have here. Okay, so let's go ahead, let's see the first one. Okay, all right, so we have the first equation here. We have the first equation that describes then the decomposition of sulfuric acid. We were told then that we start out, let's go ahead and do this here. Let me go ahead and change this here. We're starting out when then, and if we're gonna use, let's go ahead and interpret in terms of moles first. Okay, we have then 1 mole, 2 moles of H2 SO4. Okay, so we get this information directly from the balance equation. There's the 2, and that's how we know we started out with 2. When we so with that said, then when 2 moles of H2SO4 decomposes, we will form then 2 moles. Sorry, 2 moles of water. Okay, we will form 1 mole of oxygen, and this is diatomic oxygen. The 2 moles come from the balanced equation here, from the coefficients, and then we will form 2 moles of sulfur dioxide. Okay, so 2, 2, 1, 2. There it is, folks. These are the ratios. These are the numbers taken directly from the balanced equation. It gives us the amounts. So the balanced equation gives us the amounts of moles of each one of these particles in the balanced equation. Okay. And so with that said, then we want to obtain masses. We want to be able to get the masses from these from balanced equations as well, because again, we can't measure out moles, but we can measure out masses. And so we have to do a simple conversion here, okay, to obtain the mass in terms of grams of each one of these. And so basically what we're starting out here with is that if we're given the moles of a given substance, and we find the mass. So the conversion here involves a moles to mass conversion, and we're going to do the same for all of these here. Now, obviously, the difference then for each one of these conversions, the process will be exactly the same, but the difference then will be in the conversion factor. The conversion factor for each one of these will be a molar mass, but the molar mass will be different because the molar mass is unique for each one of these compounds. So the molar mass here, so how do we find what's the conversion factor for the first conversion here? We need the molar mass of H2SO4. And how do we obtain the molar mass of H2SO4? We add the masses of all these atoms together. So it's the mass of 2 hydrogens, 1 sulfur, and 4 oxygens. Okay? And so you would get then 98 grams per mole. And so we would set it up then with 98 on top, 98 grams of H2SO4 over 1 mole of H2SO4. The reason why the unit mole stays on the bottom is that then we can cancel out this here and that unit there. And so we end up with grams on both sides. And so all this hopefully is review for you folks. And so when you do that, then you end up with an answer that is 196 grams of H2SO4. So 2 moles so that means then what we're saying here then is we need to start out with them with 2, this reaction describes then that we need to start out with 2 moles of H2SO4, and that's equivalent to 196 grams of H2SO4 of sulfuric acid. Okay, all right, let's go ahead and do the same thing for the remaining 3. Okay, so the molar mass of water is going to be 1 oxygen, 2 hydrogen, which is going to be then 18 grams per mole. And if you get this, if you put this into calculator, then you'd end up with 36 grams of water. Okay, all right, doing the same thing with oxygen then. So oxygen is 2 oxygens here. Remember, this is diatomic oxygen, so that's going to be 32 grams of oxygen, sorry, for every 1 mole. Right, and so with that said, then you'd end up with 32 grams of oxygen. Right, and then finally with sulfur dioxide, then you add 1 sulfur, 2 oxygens together, you're going to get then 64 grams per mole. So we'll put the 64 grams on the top over 1 mole of SO2. And then you'd end up here with 128 grams of sulfur dioxide. Okay. All right, so what is this telling us then? It's basically telling us then, if you want to think about it in this way, all right, let me go ahead and do this here. Okay. We are starting out, if we start out with 196 grams of H2SO4, and it breaks down, it will form then 36 grams of water, okay, 32 grams of oxygen, and 128 grams of sulfur dioxide. That's exactly what we're being told here. Okay, so if you understand that, then you can see then that we can take the coefficients here from the balanced equation, obtain masses for each one of these components of the reaction itself. Okay, so essentially, again, what we've just calculated for here is that the equation is telling us then that if we start out with 196 grams of this reactant, we will form this amount of water, this amount of oxygen, and this amount of sulfur dioxide. Okay, all right, very good. Now, one last thing I want to point out before we go on is that if you notice here, well, I want you to notice something here. If you take this mass here and add it to this mass, and take all that and add it to this mass here, that means get the sum of everything on the right-hand side, you're going to see then that it will equal 196. So therefore, this shows us, and we will talk about this in just a moment after you finish this. This is what we refer to as conservation. So this is conservation of mass. Okay. Now, if you notice then, the number of moles do not add up. We start out with 2 moles here, we end up with 5 moles here. So the number of moles do not equal one another, but the masses have to equal one another, and that's what the law of conservation of mass basically stipulates. And the law of conservation of mass is a fundamental law of the universe, folks, and that is when we talk about how processes happen, all processes conserve matter, and more broadly, when we talk about it in terms of physics, we talk about this as conservation of energy, and that's the first and fundamental law, the first fundamental law of the universe. That we refer to as the first law of thermodynamics. Okay? So that's a fundamental law that everything has to adhere to in the universe, and we see that here. We saw also then that atoms, remember, are conserved. And so atoms, if atoms represent the simplest form of matter that the simplest form of unique matter that we can get, then when you add those masses together, they should also be equal on both sides. And so conservation of mass applies to conservation of atoms, but it also applies here to conservation of mass as well. Okay. All right. Very good. So make sure you write this down, folks. Okay, and check your answers with what we did here. So let's continue on. Let's continue on, and let's take a look at the next problem. Okay. So we did. I asked you to do this as well. So let's go ahead and let's work this one out together. Okay. All right. So let's go do the same thing. We start out with 2 moles. So if you take a look at the balance equation, then we start out with 2 moles of aluminum. Okay. From the balance equation, so that's the 2 moles here. We have 3 moles of sulfuric acid, H2SO4. Okay. We will produce 3 moles of hydrogen, H2. Okay, and 1 mole, and because it's not written there, 1 mole of aluminum sulfate. Okay, so that's what we have here. So again, if you notice here, if you add up the coefficients of both sides, they do not add up. You start out with 5 moles of reactants, but you only end up with 4 moles of product. Okay? All right, so with that said, then that we have identified the number of moles. Let's go ahead then and let's calculate for the masses. Okay, so we got to calculate now. So if you want mass information, you got to calculate. You cannot get it directly from the balance equation. You can get the number of particles, molecules. You can get the number of moles. But with atoms and with masses, you have to calculate for. So in order to get the mass of aluminum, we're going to have to use the molar mass of aluminum. And so you get that from the periodic table. Okay. We need the molar mass of sulfuric acid, which we calculated for in the previous problem, which you can also use the periodic table to obtain. To get the molar mass, to get the mass of hydrogen, we will need the molar mass of hydrogen, which I think would be fairly simple to obtain. And the same thing with the like the mass of aluminum sulfate. Okay. We need the molar mass here. Okay, so I'm going to leave it up to you to real quick if you to find these molar masses and calculate them for yourselves. We learned that in chapter 10. If you still have having issues with getting the molar masses, please make sure you come by and see me. But with that said, then remember, we're not trying to find the molar mass of 2 moles of aluminum. We just want the molar mass of 1 aluminum. Okay, so the molar mass of aluminum then is going to be 27 grams. I mean, we end up doubling it anyway, but the mass of 1 mole of aluminum is going to be 27 grams of aluminum for every 1 mole. Remember, with the conversion factors, these are all unit ratios, which means then the denominator, one of the parts, half of the ratio has to be 1. Okay, it's going to be out of 1 always. Okay, so make sure you keep that in mind. All right, and so with that said, now let's go ahead and fill in. With that said, we have then 54 grams of aluminum. All right, with sulfuric acid, we saw that the last time it's 98, so it's going to be 98 grams of H2SO4 over 1 mole of H2SO4. And this time then we have 294 grams of sulfuric acid. Okay, hydrogen, then that should be pretty simple. That'll be 2 grams of H2 for every 1 mole of H2. So therefore this will be 6 grams of hydrogen. And then finally with aluminum sulfate, when you add all those atoms together, 2 aluminums, remember here the 3 has to be distributed, 3 sulfurs and 12 oxygens. When you add them together, you get a molar mass of 342 grams, okay, of Al2SO43 for every 1 mole of Al2SO43, right? And so we have then 342 grams of aluminum sulfate. And again, let's do the same thing. Let's take a look at what we have here. So what basically these numbers are telling us then is if we start out with 54 grams of aluminum and we react it with 294 grams of sulfuric acid, we will produce on the right hand side here 6 grams of hydrogen and 342 grams of aluminum sulfate. If you add both sides up, folks, if you add both sides up, you should end up with 348 on both sides. And so therefore you have conservation of mass. So again, you will conserve, okay, matter. So you will conserve mass. Okay, the matter will be conserved, and you need to make sure you confirm that. Okay. All right. Very good, folks. So make sure then, if you have questions about how we do these conversions, you come by and you see me, get help with this, because this is what we're going to be doing moving forward. So you need to be able to understand how to do these conversions, review it in chapter 10, and then come by and see me if you need extra help with this. Okay. All right. Let's go ahead then, and let's move on then. Okay. All right. So what we can also do, so we know now how to obtain information about masses. So that's fairly simple. We can weigh everything out. I mean, everything can be weighed out. It's fairly simple to do for most of the reactants, most of the substances. However, if we have substances that are liquids or we have substances that are gases, then it may be a little bit more efficient to weigh out, instead of weighing out the liquids and the gases, maybe we can determine the volume. Okay? Now with liquids, it's a little bit more difficult, because with liquids then, with liquids, it's a little bit more straightforward. You can just weigh those out pretty easily. Liquids, remember, have definite volume and indefinite shape. So we can actually get the volumes there by just measuring out we get the masses by measuring out a volume in graduated cylinder and converting that to masses by using density. Okay. The problem then is, and furthermore, liquids, their volumes don't change with temperature or with temperature. Okay, so with that said, or pressure. And so with that said, then liquids are pretty easy to deal with. The gases are the ones that will always be the issue for us. The gases will be a little bit harder for us to deal with. Okay? And so what we do then is with gases, and so if a reaction involves gases, we have to be able to, we can measure out the masses if we want to. That's doable, but it's a little bit more cumbersome, and it's a little bit more difficult to get done. If we can somehow obtain volumes from the balance equation, then it becomes a little bit more easy to work with. Okay, so what we want to be able to do here is we want to be able to determine volumes from the balance equation in very much the same way we were able to determine masses from the balance equation from the previous example and what we did yesterday. Okay, all right, so let's take a look at an example here of a reaction that we've been working with. Okay, and so this is the reaction here involving nitrogen and hydrogen, where they come together and they form ammonia. So we have then here, remember, 1. So this is understood to be 1. Okay, so let's go ahead and write out the number of moles here. Okay. Let's write out the number of moles first here. Okay. All right, so let's go ahead then and let's take a look at what we have. Okay. So we start out then with 1 mole of nitrogen. Okay. 3 moles of hydrogen gas, and we form 2 moles of ammonia. Okay, so pretty straightforward. Done that, we got that. Okay. However, we want to be able to obtain volumes from this. Now, hopefully you remember then what the conversion factor we will need to do. So we can't get volumes directly from the balance equation. So we have to convert in very much the same way we had to convert with masses. Okay? However, these are masses. And so with that said, these are volumes, I'm sorry. So with that said then, what do we have to do? Well, we need a conversion factor that will relate for us moles of a gas, okay, moles of a gas, okay, to the volume of a gas. Okay? And do we have such a conversion factor? We do. Okay, and it's highlighted for us here. Okay, and I'm going to write it down for you. We know then that 1 mole of a gas, 1 mole of a gas is always going to occupy 22.4 liters of the gas. Okay, and we know that this is always true for a gas and only true for a gas if this gas is at STP. And remember, STP represents a temperature, a specific temperature, which is 0 degrees Celsius, and a specific pressure, which is 1 atmosphere. And 1 atmosphere. And we'll talk about pressures and temperatures for gases in the next 2 chapters. Okay, and we'll probably finish out the year with the next 2 chapters. Okay, but we do know this. So as long as the gas is at STP, this relationship will always be true. And that we learned back in chapter 10. So there it is, folks. There is our means of converting then moles of a gas to volume of that gas, okay? And so we can use that to find the volume of nitrogen. We can use this conversion factor to find the volume of hydrogen, and we can use that to find the volume of ammonia as well. And as long as all of these are gases and if the conditions are at STP, folks, we can go ahead and do that. So let's go ahead and let's substitute that in. Let's go ahead and substitute each one of these, this conversion factor into each of these calculations here, and then we'll get that done. So we'll go ahead and we'll plug in 22.4 liters of nitrogen over 1 mole of nitrogen. Okay. We'll plug that in, and then we end up here then with 22.4 liters. Okay. Do the same thing for the hydrogen. We're going to plug in 22.4 liters of hydrogen for every 1 mole of hydrogen, and we get there then 67.2 liters. Okay. And then finally then we'll do the same thing, 22.4 liters of ammonia for every 1 mole of ammonia. Okay, we end up with 94.8. I'm sorry, that doesn't, 44.8, sorry. Sorry, folks, 44.8. Okay, all right. So we have then our volumes. Okay, so this ends up being the volumes of the reactants product. So let's go ahead and let's take a look at what these numbers mean. Okay, and I'll finish up with this. This means then if we start out, if we measure out 22.4 liters of nitrogen, and we combine it together with 67.2 liters of hydrogen, we will form 44.8 liters of ammonia. That's what the reaction tells us once we have factored in these volumes here, okay? And what you'll notice here, folks, is that the volumes, when you add them together on both sides, they are not equal, okay? So volumes are not conserved in this particular regard, okay? All right, so with that said, then what we'll do tomorrow is we're gonna finish up with this discussion of volumes. Okay. And I would like to go ahead and start the second section of this chapter where we talk about mole ratios and actually get into the first set of stoichiometric calculations tomorrow. Okay. All right. So with that said, then take a look at this, combine CME. If you have any questions, obviously there wasn't any problems that I asked you to turn in, so there's nothing to turn in for this lecture today. But make sure you watch it, and then if you have any questions, come on by and I'm sorry. Make sure, I apologize, make sure you post the material from the practice problem that we did. Just make sure you show me that work, post that work, and then you'll be done with the lecture for today. Okay. All right, folks. If I don't see you this afternoon, I will see you tomorrow. Have a good day.